Hi, welcome to our course on Big Data from Advonics. I am Murali and I will be your instructor for this course. In this course, you are going to learn Apache Pig. What is Apache Pig? As per the definition from Apache, Apache Pig is a platform for analyzing large datasets that consists of a high-level language for expressing data analysis programs coupled with infrastructure for evaluating these programs. The salient property of Pig programs is that their structure is amenable to substantial parallelization, which in turn enables them to handle very large datasets. Apache Pig is an abstraction over MapReduce, I would say. It is a tool or a platform which is used to analyze large datasets of representing them as data flows. Pig is generally used with Hadoop. We can perform all the data manipulation operations in Hadoop using Pig. It is a data access engine which interacts with data stored in the Hadoop cluster. Let us look at the origins of Pig. In 2006, Apache Pig was developed as a research project at Yahoo, mainly to create and execute MapReduce jobs on every dataset. In 2007, Apache Pig was open-sourced via Apache Incubator. And in 2008, the first release of Apache Pig came out. And finally, in 2010, it graduated as a top-level project. Let's see what actually Pig does. Apache Pig allows Hadoop users to write complex MapReduce transformations using a simple scripting language called Pig Latin. Pig translates this Pig Latin script into MapReduce jobs so that it can be executed within the yarn for access to a single dataset stored in the Hadoop distributed file system, which is HDFS. To analyze data using Pig, programmers need to write scripts using Pig Latin language. All these scripts are internally converted to map and reduce tasks. Apache Pig has a component known as Pig Engine that accepts these Latin scripts as input and converts those scripts into MapReduce jobs. Well, now that we have known something about Pig, we should also know what is the need of Apache Pig when MapReduce and all other engines do exist. Developers who are not good at Java and who struggle with Hadoop and working with MapReduce tasks, Pig is really beneficial for them. Without having to write complex codes in Java, the Latin script comes very handy and easy to write and maintain the code. And the performance is on par with MapReduce, and there need not be any deployments of codes. Hence, ad hoc processing can be done easily. There are many built-in operators like join, filter, sort, group, etc. Pig also provides the ability to write user-defined functions in other languages like Java, Python, Ruby, etc. and invoke them from the Pig scripts. Another great benefit is because the system automatically optimizes the execution of Pig jobs, developers or users can only focus on the code semantics. Someone might still think if MapReduce already exists and what is the need of Pig. We should know that Pig is a high-level language and MapReduce is a low-level and it's a rigid language. Pig is mainly used by data scientists for performing tasks involving ad hoc processing. It is extensively used to process huge data sources such as weblogs and data processing for search platforms. Let us now look at how Pig really works. Pig runs on Apache Hadoop Yarn and makes use of MapReduce and the Hadoop distributed file system. Pig Latin we know, which abstracts from the Java MapReduce idiom into a form similar to SQL. While SQL is designed to query the data, Pig Latin allows you to write a data flow that describes how your data will be transformed, such as aggregate, join, and sort. The user can run Pig in two modes, using either the Pig command or the Java command. In the MapReduce mode, Pig job runs a series of MapReduce jobs, and this is the default mode. In local mode, entire Pig job runs as a single JVM process, and all the files are installed and run using a local host and a file system. We should know that at Yahoo, 40% of all the Hadoop jobs are run with Pig. We shall look at the architecture of Pig now. Pig scripts can be executed using grunt shells or Pig Server or in embedded mode. Grunt mode is interactive and helpful in testing syntax checks and ad hoc data exploration. Script mode runs a set of instructions from a file which is similar to a SQL script. And in embedded mode, Pig scripts can be executed from other Java programs. After the execution, scripts will be going through a series of transformations applied by the Pig framework. Parser component converts the Pig Latin to a logical plan. A logical plan is a directed acyclic graph, a DAG, which represents the statements and operators. Optimizer then optimizes this logical plan internally. And we have a compiler which would convert this logical plan to a physical plan and then try to reduce to a MapReduce plan. Execution engine would finally execute the sorted MapReduce jobs. This is the end of our presentation on Apache Pig. We have a short quiz in the next slide here to see if you have understood the presentation. What is the need of Apache Pig? And what is the difference between Pig and MapReduce? And what are the two different modes of Pig script execution? I assume you can easily answer these questions from our presentation. And this is the end of our presentation. I hope you all have understood and liked this presentation. And keep watching more related videos from Advonics. Thank you. Hi. Welcome to our course on Big Data from Advonics. I am Murali and I will be your instructor for this course. In this course, you are going to learn about Hadoop, MapReduce and Yarn. As per definition, MapReduce is a programming model and an associated implementation for processing and generating large datasets with a parallel distributed algorithm on a cluster. Yarn is the prerequisite for enterprise Hadoop, providing resource management and a central platform to deliver consistent operations, security, and data governance tools across Hadoop clusters. Yarn also extends the power of Hadoop to incumbent and new technologies found within the data center so that they can take advantage of cost-effective, linear scale storage and processing. It provides developers a consistent framework for writing data access applications that run in Hadoop. Coming back to MapReduce, it is a software framework for easily writing applications which process vast amounts of data on commodity hardware in a reliable and fault-tolerant manner. MapReduce is useful for batch processing on terabytes or even petabytes of data which is stored in Apache Hadoop. Few benefits which we see are developers can easily write applications in their language of choice such as Java, C++ or Python, and MapReduce jobs are easy to run. MapReduce can process petabytes of data which is stored in HDFS on one cluster. MapReduce takes care of failures. If a machine with one copy of the data is unavailable, another machine has a copy of the same key-value pair which can be used to solve the same subtask. Earlier, the job tracker used to keep track of this all, but now it is the yarn which does everything for now. MapReduce moves compute processes to the data on HDFS and not the other way around. Processing tasks can occur on the physical node where the data resides. This significantly reduces the network I/O patterns and contributes to the Hadoop's processing speed. Let's now look at how MapReduce works. A MapReduce job usually splits the input dataset into independent chunks, which are processed by the map tasks in a completely parallel manner. The framework sorts the outputs of the maps, which are then input to the reduce tasks. Typically, both the input and the output of the job are stored in a file system. The framework takes care of the scheduling tasks, monitoring them, and re-executes the failed tasks. A MapReduce job splits a large dataset into independent chunks and organizes them into key-value pairs for parallel processing. This parallel processing improves the speed and the reliability of the cluster, returning solutions more quickly and with greater reliability. The map function divides the input into ranges by the input format and creates a map task for each range in the input. It is very important for us to understand this part. The output of each map task is partitioned into a group of key-value pairs for each reduce. The reduce function then collects the various results and combines them to answer the large problem that the master node needs to solve. Each reduce pulls the relevant partition from the machines where the maps executed, then writes its output back into HDFS. Thus, the reduce is able to collect the data from all the maps for the keys and combine them finally to solve the problem. During a MapReduce job, Hadoop sends the map and reduce tasks to the appropriate servers in the cluster. The MapReduce framework operates on the key-value pairs. That is, the framework views the input to the job as a set of key and value pairs and produces a set of key-value pairs as the output of the job finally. And the result output could be in a different format. The key and the value classes should be in a serialized manner by the framework and hence need to implement the writable interface. Additionally, the key classes have to implement the writable or comparable interface to facilitate sorting by the framework. Input and output types of a MapReduce job typically have a key and value pairs, which are finally reduced to another key and value pairs. I hope you have understood now how MapReduce works. Let us now look at yarn in relation with the MapReduce. Yarn's original purpose was to split up the two major responsibilities of the job tracker, task tracker from Hadoop 1 into separate entities. But the fundamental idea of yarn is to split up the functionalities of resource management and job scheduling monitoring into separate daemons. This is part of Hadoop 2. We have a global resource manager and per application an application master. An application is either a single job or a directed acyclic graph of jobs. The resource manager and the node manager formed the new generic system for managing the applications in a distributed manner. The resource manager is the ultimate authority that arbitrates resources among all applications in the system. And the application master is the framework-specific entity that negotiates the resources from the resource manager and finally works with the node managers to execute and monitor the component tasks. The resource manager has a scheduler, which is responsible for allocating resources to the various applications running in the cluster, according to the constraints such as queue capacities and user limits. Each application master has responsibility for negotiating appropriate resource containers from the scheduler, tracking their status, and monitoring their progress. From the system perspective, the application master runs as a normal container. The scheduler is responsible for allocating resources to the various running applications which are subject to familiar constraints of capacities, queues, etc. The scheduler is a pure scheduler in the sense that it performs no monitoring or tracking of the status for the application. But it also offers no guarantees about restarting failed tasks either due to the application failure or hardware failures. The scheduler performs its scheduling function just based on the resource requirements of the applications. It does so based on the abstract notion of a resource container which incorporates elements such as memory, CPU, disk, and network, and so on. Let us now understand a word count example execution in a MapReduce way. Word count is a typical example where Hadoop MapReduce developers start their hands-on with. This sample MapReduce is intended to count the number of occurrences of each word in the provided input files. The word count operation takes place in two stages, a mapper phase and a reducer phase. In mapper phase, the content is tokenized into words, then we form a key value pair with these words, where the key being the word itself and the value being 1. So words coming from first split here, for example the deer, bear and river, each are assigned a value of 1, and similarly for other splits. In the reduce phase, the keys are grouped together and the values for similar keys are added. So here there are only one pair of similar keys. For example, bear, the values for these keys would be added to the output key value pairs would be bear 2, car 3, deer 2 and river having 2 occurrences. The point to be noted here is that first the mapper class executes completely on the entire dataset, splitting the words and forming the initial key value pairs. Only after this entire process is completed, the reducer starts its work. I hope you have clearly understood how a MapReduce job works on this word count example. We have a short quiz in our next slide to see if you have understood the presentation. What is the role of a scheduler? And how is Hadoop 1 different from Hadoop 2? Or what are the new features which Hadoop 2 brought in? And when does the reducer phase start its work? This is the end of the presentation, and I hope you all have understood and liked the presentation. Keep watching more related videos from Advonics. Thank you. Hi, welcome to our course on Big Data from Advonics. I am Murali and I will be your instructor for this course. In this course, you are going to learn Hadoop MapReduceHandsOn. Let us now look at this program. It is a word count Java program which results in the number of occurrences of each word from the input file. In this MapReduce program, we have two important methods, one for map and one for reduce. The main method would invoke the map and reduce methods. But for ease of development and convenience, we have written here two individual classes for map and reduce. This is one for map and one for reduce. We can also write an individual driver class separately, but here we have mentioned all in one main method. In this method, we define all the configurations required, and it triggers the map and the reducer classes. Configuration information includes the name of the job, the mapper class, the reducer class, and the input and output types. So here we are mentioning what is the output type and output key and value types, and also the input and output files as the arguments here. Let us now look at the mapper class. The data types provided here are Hadoop specific data types designed for operational efficiency and suited for massive parallel and lightning fast read-write operations. All these data types are based out of Java data types itself. For example, a long writable is the equivalent for long in Java and an int writable for int and text for string. These arguments refer to the data type of input and output key value pairs specific to the mapper, or rather the map method. So in our example, the input to a mapper is a single line. So this text, which is one input line, forms the input value. And the input key would be a value assigned in default based on the position of the text in the input file. Our output from the mapper is of the format like a word and a count of it, and which is number 1. Hence the data type of the output key value pair is a string and an integer. Let us now look at the map method. The first and second parameters, which are the input parameters, which refer to the input key and the value to the mapper itself. And the third parameter is a context object. This context object allows the mapper and the reducer both to interact with the rest of the Hadoop system. It includes configuration data for the job as well as interfaces which allow it to emit the output. Applications can use the context to report the progress or to set up application level status messages or update counters or indicate that they are alive, and also to get the values that are stored in the job configuration across the MapReduce phase. And this context object, finally, it unifies the role of job configuration, output collector and reporter, which were used in old API. Now let us look at this actual map method itself. The implementation of this map method is we are converting the input line from a text to a string here. If you see here, the input text is converted to a string, and here we are defining one int writable variable which is of value 1. Using a tokenizer to split all the lines into words. So this line is split into individual words here. And here we are iterating through each word and we are forming a key value pairs. And finally we are assigning each value from the tokenizer to the text word. we finally form the key value pairs of each word. As you see here, the actual word is the key and 1, which is the result of this object 1. So for example, if we have this line is the input, so we see this as the key and value 1 as the value, and then we would be having is as the key and value as 1, a as the key and value as 1. So and here again we are encountering the same word this, so still we would be having one more key with this and value as the 1. So this would be the output of this particular map method. Let us now look at the reducer part. In the parameters, the first two refer to the data type of input key and the value, which are the input key and the value to the reducer, and the last two refer to the data types of the output key and the output value. Earlier, the mapper emits outputs which are like this and 1, this and 1, is and 1, and so on, right? Now this is the input for the reducer. So here the data types of the key and value in the Java would be string and int, which are the equivalent in Hadoop would be text and int writable. Also we get the output as the word and the number of occurrences. So the data type of the output key value would be text and int writable. So this is our output going to be, which is the text and one more integer. The input to the reduce method from the mapper after the sort and shuffle phase would be the key with the list of associated values with it. So for this particular method, it is the key and the list of all the associated values with it. So let's say for this particular method, we would be getting this 1 and also this 1. So they are all shuffled and sorted, so that when we go through this iterable, we just keep counting here in the actual method. So as mentioned earlier, the input to this reducer instance is a key and the list of values. Hence, we have a text key and an iterator of all the values. And the third parameter we know, which is the context object, which is storing all the key and value pairs, and of course it does many such things. And in the actual reduce method itself, we are finding the sum of each values and writing it into the context final result object. So this is the program which has two main classes, the mapper class and the reducer class. So mapper is creating all the keys and values with each of them assigned to value 1, and the reducer is before even the reducer is getting invoked, it gets all the keys and values are shuffled and sorted, and finally the results are sent to the reducer class. Now in the reducer class, we get an iterable of all the values for that particular key, and those values we are summing it here and putting in the result object. So this is the actual program. Let's look at the imports which are part of Hadoop core and the MapReduce specific libraries. And of course we are also using Java util and IO for file readings. We should to configure this in NetBeans, we will be using a POM file. So POM stands for project object model. Here you see we have mentioned two dependencies, one for Hadoop core and one for the actual MapReduce client libraries. So in Hadoop, the MapReduce process creates the output directly in HDFS and stores the output files onto the same. So let us take a look. So now that our program is ready, so we can build it from here. So let's try to build it. Let's do a clean build. Okay, our build is successful here. but at the same time, maybe in Eclipse, if you are trying to do if you right click on the project, we can use an export utility to create the actual distributable. But for now, our distributable is already created. We can take that and copy it onto the Hadoop server. Let us now copy this Hadoop jar file which is generated from our NetBeans project to the Hadoop servers. I am currently at our Hadoop home directory, and from there we are at share Hadoop MapReduce directory. So here we are going to copy it. Okay, it is now copied. Let's try to execute that. So before executing our word count program, make sure we start the servers. So I have already started the servers. Let's see if they are running. You can type JPS and you see all the nodes are now running. We have already tried to create how to make DAR on Hadoop server. So we are going to do that the same thing again. So we need two directories, one for input, one for output, and we will copy one file to the server, and we will give that as an input to our word count program. Okay, I'm going to create one input directory in Hadoop and one for output as well. Okay, we have two directories. So what we are going to do, we are going to copy this local file readme.txt onto the input file, onto the input directory. Let's see, copying that file. So that is going to be our input. So with this command, we are going to run our word count program. What did we give here? Our first command is bin Hadoop. So with this Hadoop command, we are giving input as the jar file. So our jar file is which we have already placed it here. So and the actual class name is the word count, because if you see in our program, so this is our word count which is part of this package, and the input is our readme text file, and the output is going to be in the output directory. So let's see what's going to do. And it's now executed. We can see that it started with 0 0, and then the mapping is done, and finally also the reducing is done, and we should be seeing the output now. Let's look at let's list out with this ls command what's there in that output directory, and let's try to do a cat on that. It has actually created let's do word count. So probably there are some other files inside that. So these are the two files which you would be seeing. So one is a success file with 0 bytes, and the other one is the actual result. So let's try to open this file. We will do a cat. And finally we are seeing all the results. So what are the number of occurrences of every word in the readme text file? Yeah. So export is there twice, and so on. Okay, to summarize what we have done, we have written our word count program which has a mapper class, which has a reducer class, and all the driver class information, which we have put everything in our main method. And this main method invokes the actual program with this all these inputs, and we have built the project from here. We copied it onto the Hadoop server where all the libraries are there, and there we try to run our program, and we notice that all the output is written into this output directory. I have a short question here. I hope you have understood what is this question. I would just like to know what is the sequence of this MapReduce algorithm. I hope you have understood this already. So this is the end of our presentation. I hope you like our presentation and keep watching more videos from Edonics. Thank you.